Hello and welcome. This is our first physics video, the first video we are going to have on our physics series, and more videos are coming, and it's going to be an exciting and a very informative class. So you are going to enjoy every bit of it. So I promise you that. So I encourage you to invite your friends, your colleagues, and all your loved ones. Let them come here and join us, bring them here, because guess what? This is where it is happening. This is where the learning is happening. So let's dive in. Today we will be discussing a very interesting aspect of physics that is known as mechanics. A very interesting aspect of physics, that is mechanics. Of course, mechanics is the branch of physics that studies motion, force, and energy of bodies. So it is interested with the motion of bodies and the cause of that motion, and in the energy that is responsible for the force. So that's what we study in mechanics. And when we are studying motion of bodies, this motion can be categorized into two. So on the study of motion of bodies, the motion can be studied under kinematics or dynamics. So these are the two aspects of the study of motion. When we are studying motion, we can study it under kinematics or dynamics. Now, kinematics is the study of motion when we are not interested in the cause of motion. So we'll be studying motion, we'll focus on how objects move. So how, our focus will be on how and not why. We are not interested in why objects move. So we'll be studying motion without respect to the forces responsible for the motion, because objects move because of forces. It is forces that are responsible for motion. So, but in kinematics, we'll be studying motion without making reference to forces. We'll ignore all the forces and focus on how the objects are moving. So we are going to discuss this. We are focusing on kinematics for today. In subsequent classes, we are going to meet dynamics, where we will study why objects move. So in under dynamics, we will see the concept of force. To study forces, how they interact with our objects, and how they cause objects to move. So, but for now, let's just focus on kinematics. So this kinematics is the branch of the study of motion that is focused on studying motion without considering why or the forces that are responsible. So everything we'll be studying this time around will be about motion, but we are not going to mention the forces that are responsible for the motion. So you can see that it's already going to be an interesting class. So now let's dive in. We will get to the terms that are associated with this kinematics, and then we will discuss them. So let's get started. In this study of kinematics, we are going to meet the following terms. First, what is motion? A body is said to be motion when that body changes its position with time. So when a body is changing where it is positioned, its location, it is changing it as time changes, that body is said to be in motion. That's just the definition. So the terms that we are going to meet under this kinematics, which is the study of motion without considering the forces responsible, the terms that we are going to meet under this kinematics are very fundamental terms, like position. When we talk about position, the position of an object is simply the location of that object in space. Where do we locate this object? So if we have an object, say A, where is this point A located? That's its position. To obtain the position of this point A, I can use the Cartesian plane by drawing the Cartesian axis, the vertical and the horizontal axis. So once I draw the Cartesian axis, which always gives me a graph, then I will trace its y coordinates, the y coordinate of this point A. I'll trace the x coordinate of the point A. So once I'm able to do that, then I've identified the position of A. So the position of an object is where it is located in space, and this location in 2 dimensions is always given by the x and the y coordinates of the graph, x and the y. So at every point in time, we identify every object or every item by using their coordinates. At this point, we'll just focus on the x and y coordinates. We'll discuss them in 2 dimensions only. We'll not go to 3-dimensional analysis. So that's the position of the object. Okay, so that's what position means. Next, we'll talk about another important term, and this term is what we call time. We always use the concept of time, but what is time? By definition, there are many definitions that can go, but one definition we can accept for time is that time is that with which events are distinguishable with respect to before or after. So time is something that distinguishes events. It arranges events in order such that one event can be distinguished from another using the concept of before and after. That's what time does. It ensures that our events are kept in order, so that we say that this happened after this and after this or before this. That's what time does. And that's why when you check your time, it says after 12 o'clock, 10 minutes after 12, that means 10 minutes after 12 o'clock, where the event is 12 o'clock and all that. So time tries to distinguish events using before and after. That's what time does. Thermodynamically, time can also be defined as the property of matter which allows it to assume more than one distinct configuration. So it is that property of matter that allows matter to take more than one distinct configuration. So with time, matter can change its configuration, although the matter may not eventually go ahead and change its configuration, but the matter has been allowed, has been given the opportunity to change its configuration. But that is in thermodynamic time, but it is still a very important. So time can be defined by various fields or various fields. So but this is what time does. Basically, it distinguishes events for us. So that's what time does. And in physics, we always use small letter t to represent time. T. Now, there are various units of time, but the SI unit, the basic unit we accept for time is the seconds, which we represent with letter S. So time for us is measured in seconds. We measure time in seconds. So when you have time given in other units, it is obligatory for you to convert the time to seconds. In most cases, you will need to do that so that you will be able to use them and solve. So pay attention to the symbol of every quantity and the unit of that quantity. So time we represent with letter T, and the symbol for that time is letter T, and the unit is letter S. That is for seconds. So we measure time in seconds, converting to convert other units of time to seconds so that we'll be able to work. Okay, so that's another concept. Then the next concept that we will have to discuss will be distance and displacement. Here we use small letter s to represent distance or displacement. It's just convention. You can use any letter you like, but here we are just using a small letter s. We are just using small letter s. So you are free. This is a dummy variable, not a convention. It's almost a dummy variable. So just use that. Now, please note that this s here is the unit of time, but this s here is the symbol for distance, so that you don't mistake them for the same. This is seconds, standing for seconds, which is unit of time, but here we are using s to represent the symbol of distance or displacement. So distance to displacement, either of them can be represented with this letter s. Okay, so what is distance and what is displacement? When we talk about distance, we describe distance as the magnitude of separation between 2 points. The magnitude or the extent of separation between 2 points. If I have 1 point and I have another one, how much they are separated is what I call distance. The extent of separation between them, if I measure the extent of separation, that's what we call the distance. So that's what we describe as distance. Extent of separation. Okay. What of displacement? What of displacement? And why am I putting both of them together? Displacement is a form of distance. In fact, in some cases we use those terms interchangeably. Displacement is distance in a specified direction. So this distance has been given a direction. So when I am interested in the distance moved in a particular direction, in a specific direction, I'll describe that as a displacement. One difference between them is that distance, while distance is a scalar quantity, displacement is a vector quantity. This is a scalar quantity, being that it has only magnitude. By representing its magnitude, it has been fully represented. But for displacement, I'll need both the magnitude and the direction to represent it. So displacement and distance can be used there. Sometimes loosely we use them interchangeably, but strictly speaking, they are not the same terms. Okay, so that's the term of interest: distance and then displacement. Okay, then we'll go to the next term, which we call speed or velocity. Why am I putting these two together again? I'll use V, small letter V, to represent this guy, speed or velocity. If I have a displacement or distance, but that distance is not maintained, this distance is changing. Like at a time I see the distance to be this, and the body has moved to another distance. In a second time I'll see the body in a new covering a new distance. After another time it has covered yet another distance. So in this case now, it implies that the distance is changing, right? Now, if I calculate, if I try to measure how this change occurs, the rate of the change, how is the change happening? This distance is changing, but how is it changing? Every time, how much change do I have? How much change do I have in the distance? Every unit time. So that will give me what I describe as speed, or to be more precise, average speed. This will produce what I call average speed. So this average speed is the rate of changing distance with time. And once we talk about rate here, you know, the rate of changing a distance. Once we talk about rate, you know, we are making reference to time, right? So it means that what we are discussing, our speed, is a distance which is symbol x, all upon the time it took for that change to occur. That is change in distance. Change in distance upon the time it took for that change to occur. The distance must be changing. This will give me the concept of average speed. Now, we have to discuss and understand this concept of speed a little bit more, because it is average. So, when we are talking about average speed, it means I have a distance at this location. This is the first distance from here, from my reference point to point 2. I have a distance covered. Then, but when I check my time, after some time, I have a new distance covered. So there is now the distance is changing. It has changed from a value of maybe 3 units, or let's say this is point A, point B, and point C. So the distance here was 0. It has not started. Here it was 2, and here 3. So the distance has changed from 2 to 3 units. So when I measure, if I want to calculate my speed, I'll now say check the time it took for this distance to change from 2 to 3. I'll check that time, and then what I'll update is what I call the average speed. Average speed. Are we together? So that average speed, no, it is the speed from here to here. It is the average of the speed between point B and C. It doesn't give me the exact value of speed at point B or the exact value of speed at point C. Are we together? So it gives me the difference or the average of the speed between point B and C. But you know, for instance, that in reality, moving from point B to C, the body might have slowed down in the middle. Maybe this is a point D now, which is between B and C. Maybe at point D, the body encountered an obstacle. And because of that obstacle, it slowed down, assuming a car that is traveling on the road, and then along the path, there was a goat ahead of it. And then it had to slow down to allow the goat to pass. Now, but I'm interested in the distance or the speed between point B and what I got is the distance or the speed between point B and C. That speed between point B and C, what I'll get there is it's just the average, because I have calculated the time it took for this body to move from B to C. But I didn't know what, maybe at that point it was slowing down. In fact, maybe at point D, its velocity is 0 because it was not moving. Maybe it stopped totally to allow the goat to pass. And because of that, it was at 0. But I wouldn't know that because I was not there at point D. I was only at point B and C. And because of that, I'm calculating the average. So the point I'm making here is that what I have here is what we call the average. That average is not an exact true value. But if I am interested in the exact value of velocity at every point in time, maybe velocity at or speed at point B, speed at point B, what is the speed at this point? Not the speed between point B and C, but speed at point B. How is it moving at point B? How? At this particular point, not between this point and this point, but at this point alone, what was happening there? And that is what will give me the concept of instantaneous speed. Speed at a point that is instantaneous. What is happening at this point? It is no longer an average value, but an instantaneous speed. And for me to calculate that, I have to invoke the concept of calculus. So in that case, my speed is going to be the t, the distance, the time. That means by calculus, the s, the t, and that will give me the speed at that point. That is the instantaneous speed. The distance, the time. This is under calculus. Are we together? So for you to understand this, you go to our mathematical series. If you don't have any knowledge of calculus, go to our mathematical series on this and then solve, understand how this is done. But for now, there is nothing to panic about. Just we will not solve, we will not focus more on calculus at this moment. So, but just know that the distance, the time, gives you a measure of the instantaneous velocity or instantaneous speed. Now, okay, you can see that you maybe you notice that I pronounced velocity and the speed interchangeably to show that they are similar terms. While speed is distance over time, velocity is displacement upon time. The difference between them is just like the difference we have here. Distance is a scalar quantity, speed is a scalar quantity. Displacement is a vector quantity, velocity is a vector quantity. So this is vector, this is scalar. That's one difference between them. So speed and velocity are just like the same term. They are similar but not exactly the same in a strict sense. So velocity requires direction to be specified. So when the direction is changing, then velocity is changing. But when the direction is not changing and the magnitude is not changing, then velocity is not changing. Speed has nothing to do with direction. Speed is only interested in the amount of magnitude of change, the magnitude of the change with time. That's the difference between them. So this is speed is changing distance over time, velocity is changing distance. We represent either velocity is changing displacement over time. We represent either of them with the same symbol, v. So this v here can mean speed, it can mean velocity. While this s here can mean distance, it can also mean displacement. Time is still time. Okay, so that is the speed and the velocity. So now what is the unit of speed or velocity? The unit of this guy is now a derived unit. How? We'll get the unit by using the units of the terms that gave birth to it. And those terms are distance or displacement. And you remember, oh, I think I forgot. I forgot to mention the unit of displacement. The unit of displacement, because it is distance or displacement, they have the same unit of meters, m. We represent them with the unit of meters. You can have multiples and sub-multiples of units like the millimeter, the kilometer, and all that. So, for the unit of displacement and this is the SI unit is the meters. Okay, so if you want to find the unit of speed or velocity, the unit of speed is we have meter on top for displacement, and we have seconds for time under. So it means that the unit of this guy is meter over time, and the meter over time can be written as meter per seconds, or you simply write it as ms raised to power minus 1. Remember, when you have to power negative, it shows that this guy is under, it's a denominator. So this is meter per second, meter per second. You can write it this way or this way. So it is a derived unit. How we got it is from this is distance in meters, time in seconds. And that's how the unit of distance or the unit of speed or velocity is meter per second. It is very important to take note of these units. And then we'll also highlight this particular equation. It is important to keep note of this equation So I can call it equation I. All the equations are put in boxes are highly relevant equations. We'll keep them because we always make reference to those equations. So I'll call this equation I because we are going to use it later. And we'll use them to solve problems. So take note of this equation. Make sure you are jotting down all these equations, especially the ones I have in boxes. Jot them down because you will make reference to them later. Okay, so velocity is distance over time. Speed is velocity is displacement over time. Speed is distance over time. The unit is of either of them is meter per second, right? And that's what we have just discovered. Now, it means I can actually plot if I have a body that is moving, I can find its displacement, I can measure its displacement and calculate the time it took for that displacement, and then I'll use this to plot a graph. I can plot a graph from it, and that graph is a displacement or distance on the vertical axis, while time is on the horizontal axis. So for such graph, we call it displacement time graph or distance time graph. When we have such a graph, for specific motions or for some certain motions, you have situations where you are having straight lines or curves or whatever. So the interpretation of such situations is that if I have a straight line that is sloping upwards, what does it mean? Remember, for such displacement time graph, if I'm able to calculate the slope of the graph, slope is change in y upon change in x, right? Change in y in this case will give me the displacement, and change in x in this case will give me the time. So the slope of the displacement time graph, if I find the slope, it will give me the velocity of that body. So the slope of displacement time graph produces a velocity. Now, this point where I'm having straight line, the implication is that the distance or the displacement is changing, but it is changing uniformly. So there is a uniform change in the displacement. So when the displacement is changing uniformly with time, as time is changing, it will give rise to what we call uniform velocity or constant velocity. We can call it constant velocity or uniform velocity if we are talking about displacement. If it is distance time graph, then this region will give me uniform or constant speed. So it will give rise to what we call constant or uniform speed or velocity, depending on whether this is displacement or distance. So the constant speed or the constant distance occurs when the change in displacement is the same over the period of time. No matter how little the period of time is, so long as the change in displacement is the same. It is not, the displacement is changing, but it is not changing on how it is changing. Like the displacement is increasing, like it is increasing in displacement, but after every little interval of time, the change I obtained in the previous displacement is the change I obtained in the next displacement. Do you understand? So this will give rise to constant or uniform velocity or constant or uniform speed. So we should know that. Now at this region where there is curve, this curved region shows where the displacement is changing as it is changing. So it is no longer uniform. The displacement is not changing uniformly, but it is changing non-uniformly. The way the displacement is changing is, or the way it changed in the previous time is not how it will change in the next time. So it is a non-uniform change. So this non-uniform change of a displacement will give rise to what we call acceleration. At that point, the body is accelerating. In this region, the body is not accelerating. It's having a uniform velocity. It is not accelerating. But here, it is changing how it is changing. So the body is now accelerating. So within this region, the body is changing how the displacement is changing how it is changing. So, and that will give rise to the next term we are discussing or we'll meet, which is acceleration. Now, what is acceleration? Acceleration is the rate of change in velocity. Remember what I told you, that if displacement is changing, it gives velocity. But that velocity can be uniform or constant. If the change in displacement is the same, then it will give rise to constant velocity. But if the change in displacement is not the same, then it means that the velocity that we are having is even changing. So there will be a change in velocity. So acceleration is a change in velocity over time. Now in this case, we are going to use other terms to represent the change in velocity. So we are having v minus u all upon t. Here, v and u represent velocity. But why we are using different terms for them is to show that the velocities are not the same. The velocities have changed. Initially it was u, and finally it became v. So the velocity has changed from a value u to a value v. Do you understand? So this is now a changing velocity. The velocity is no longer constant. It is no longer uniform. It is now a changing velocity. So when there is a changing velocity, then it gives rise to acceleration. So remember that we discussed before that acceleration or speed, which we write as v, is distance upon time, which we wrote by calculus as the s, the t, right? Now, if this distance is changing, the way it is changing, like if there is a change in distance, a second change in the distance, then we'll now have this concept of acceleration where it is the squared s, the t squared by calculus. The squared s, the t squared. So this is a second derivative of this. So it means that acceleration is the second derivative of displacement. So a changing velocity is what a changing displacement is what we call acceleration. So acceleration by calculus is that is instantaneous acceleration, because what I'll get here is an average value of the acceleration. So but when I'm talking about the instantaneous acceleration, then the instantaneous acceleration will be the squared s, the t squared. Now, it doesn't just end here. Of course, these are numbers. Acceleration can equally be changing. I will follow it. So there can be a situation where the acceleration is changing, and so it is no longer that the velocity, that the displacement is changing. You know, when the displacement is changing, it gives rise to velocity, and when the velocity is changing, it gives rise to acceleration. But when the acceleration is even changing, it gives rise to another term, which we call the jerk, which is the third derivative of displacement. So we have the third derivative s prime prime prime, the third derivative of displacement, which we call the cubed s, the t cubed. That is the third derivative of this. It is called the jerk. it is a quantity we call jerk. So jerk is a changing acceleration. So when acceleration is changing, it gives rise to jerk, right? Now, it doesn't stop there. Jerk can also change when we talk about the fourth derivative of this displacement with time, which is the derivative of jerk. So this time it is going to be s prime 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 prime, the fourth one, right? But into four places, that is the fourth derivative. It becomes d to the power 4 of s dt to the power 4. That is the fourth derivative, which is called the snap, also called the jamb. So that is the derivative of jerk. Remember, jerk is derivative of acceleration, and acceleration is the derivative of velocity. So now snap or jamb is the derivative of jerk. And this continues on and on, that we can equally talk about the fifth derivative, s1, 2, 3, 4, 5, right? Which is the 5 s to the power 5, the t to the power 5, right? So the fifth derivative of this is called the crackle, right? Crackle. So, and that's how it continues. We can talk about the sixth value, the sixth derivative, which is the d to the power 6 of s dt to the power 6, which is the fourth. So what we are driving at is that this distance or displacement can continue to change and change and change, and it will be giving rise to new values or new terms in physics. So, but this is not our concern for now. Don't worry about the pop, the crackle, the snap, the jerk. So we are just concerned with acceleration at this moment. So we'll focus on acceleration, and then most times we are not even interested in instantaneous acceleration, but the average value. So we'll focus our attention here. So this is what we want to study, the instantaneous acceleration. And so our formula here shows that acceleration is the change in velocity per time. So we can describe this as equation II, for instance. Okay, so change in velocity per time. So we can equally obtain its unit. Remember that velocity already has the unit of meter per second, as we obtained in the previous one. So velocity is already meter per second, and then the time, unit of time, is second also. So it means that the unit of acceleration now is meter per second. So at the end of the day, there will be 2s under, so this will now become meter per second squared. So which we can equally write as meter per second squared. Either this or this is okay. So it's meter per second squared for acceleration. So that's for the unit. Now we'll make use of these equations to explore motions in different directions, especially motion on different planes like horizontal, linearly accelerated motion on horizontal plane, on vertical plane, and then we'll still extend that to projectile motion. So let's enjoy the process, what we get from these equations, and see how it goes. So before we discuss these equations, let us talk about the velocity time graph. So if we obtain the instantaneous velocities of a moving body at various points and then measure the time when these velocities happen, we can use them to plot a graph of velocity against the time, and that graph will be known as the velocity time graph. So from such graph, we can go ahead and obtain different slopes. For instance, if we have a slope, an upward slope to the right, it shows, and a straight line sloping to the right, it shows that during this period that the velocity is uniform, right? So at this period, the velocity is changing uniformly, right? At every point in time, there is a change in velocity, and that velocity is uniformly increasing, or okay, in this case, it's increasing. So there is at that instance, the velocity is uniformly increasing, right? So during that period, if we find this, if we plot the slope of the graph, but we can continue to a point where we may have a flat line. A flat line indicates that the velocity is no longer changing, it is maintaining a constant value. So once the velocity is consistent, it means that at this point there is a constant velocity. And remember what constant velocity? So this point on this graph, this point of constant velocity here, will correspond to the point of positive slope on the displacement time graph. So this point on displacement time graph will correspond to this point here, while this point that is changing will correspond to this point where there is acceleration, right? So this particular let's make them give them resemblance. So this line, red line, will correspond to this red line here, right? While this particular line will correspond to the area where the body is accelerating. So here there is acceleration, but in this case, there is a linear acceleration. There is a linear acceleration. So it doesn't mean that the velocity is not changing. Here, the velocity is changing, but it is changing uniformly. So there is a uniform change in velocity. So, but it is not a uniform velocity situation. No, the velocity is changing. It is a uniform acceleration situation. Because when the velocity changes uniformly, then it means that the acceleration is uniform. There is a uniform. So this point corresponds to where there is acceleration. Whereas this particular point here, where there is a constant velocity, corresponds to this point where the distance is changing, or it is most likely to correspond to this point. Okay, so what we are saying now is that we can plot the velocity time graph, and then we can have another portion this way. So I want to describe these various portions as so we have this place, there is the velocity is increasing. So if I find the slope of this portion of the graph, the slope will give me acceleration, because it is going to be changing velocity by changing time, and that will provide me with acceleration. Now for here, there is no change in velocity, so velocity is constant, which means that if I calculate my change in velocity, even though the time is changing, but the change in velocity is the same. So what it implies is that there will be zero acceleration. So throughout this point, red portion, the body is not accelerating. In as much as the body is moving, but it is not accelerating. So there is no net force acting on the body. Now, in this region, this green line will indicate a portion where the body is actually changing in velocity, but that change in velocity is a decrease. The velocity is decreasing uniformly. So for such a uniform decrease in velocity, we call it a retardation. The body is coming to rest. You can describe it as deceleration, or you call it a retardation. So the body is decreasing in velocity uniformly, and that will give rise to retardation or deceleration. So why I'm making reference to all this is because we'll solve problems on all of that. Now let's talk about the velocity equations of linearly accelerated motion. So let's derive equations that we can use to study motion of bodies that are undergoing linear acceleration. First, we do that for when the body is in horizontal motion. So for a body that is undergoing a linear acceleration in the horizontal plane, you can generate the following equations. First, let's get our equation II, a very previous equation we derived, where we say that A is equal to V minus U all upon T. Remember that V is the final velocity, U is the initial value of the velocity, and T is time. So A is acceleration, meter per second squared. So now let's find the value of, let's rearrange these equations to obtain the value of final velocity in such a situation. So once you cross multiply, you are going to have that V minus U is equal to AT. And once you move this over to this side, you are now going to obtain that V is equal to U crosses over to become positive. So you are going to have U plus AT. So this now is one equation for a motion, a body that is undergoing linear acceleration. So this is equation for such a body. Remember, V is final velocity in meter per second, U is initial velocity in meter per second, A is acceleration in meter per second squared, and T is time in seconds. So we describe this as equation 1. Remember that all these equations that we are going to have in boxes will be very important. They will play important role. They are already very important, and we'll use them to solve extra problems. Okay, so let's go ahead and obtain a second equation. We already have equation for velocity, but recall that at the other time we mentioned that velocity is average velocity is distance upon time, right? That was equation I. So we can change this, but before we make distance the subject or displacement, before making the subject, let's find the value of this average velocity. What do you mean by average velocity? Average velocity, of course, is the velocity, some of the velocities, initial and final, divided by their number, which is 2. So in this case, average for us is V plus U all upon 2. This is the average velocity. So this guy here, this is what it actually represents, average, right? Initial and final divided by 2, that's average, right? So this is equal to S upon T. So I can go ahead and cross multiply to find the value of S, right? So if I do that, I have that 2S is equal to V plus U times T. But then I already have a value for V here. My V is U plus AT. So I can actually put the value of V here in this equation to have that 2S is equal to, my V is U plus AT, then plus U multiplying T. So I just use U plus AT to replace V here. So this is now U and U. So when you add the two U's, U and U, you get 2U, right? So 2S is equal to 2U plus AT all times T. So we used it to open the bracket so that 2S is equal to, this is 2UT plus AT squared, because T is multiplying. So you divide 2 by 2 all upon 2 upon 2, and then what you obtain is the equation again that S, this will lead to S is equal to, this cancels, and we are having UT plus half of AT squared. So this becomes a second equation that we will use, equation of motion when the body is undergoing linear acceleration, we are very welcome to use this equation, and you'll see how we apply them to problem solving. So we are having that s is equal to ut plus half at squared. That's another equation for motion. Now let's derive a second one. You can see that in this first equation, we omitted s. There was no s. But here there was s, but there was no no v, right? Now in the next equation, we'll try to derive the equation without t. So let's derive the third equation. So here we are with the next equation we want to derive. We come from, recall that a is equal to v plus u, v minus u. That's the velocity upon time. So let me make t the subject. Once you cross multiply, I have that at is v minus u, which implies that t is equal to v minus u all upon a. That's the value of our time. So let's now bring this value of time to the formula of distance. Recall that we said the average velocity, which is v plus u all upon 2, is equal to, formula for distance is distance upon time, right? Average velocity is distance upon time. So we can, making s the subject again, we'll have that 2s is equal to v plus u times t. But we already have a value of t. But before we put that, let's have that s is equal to v plus u all upon 2, because dividing through by 2 times t. So we divided by t to have this. Now let's bring the value of let's bring out the value of t here, and we'll now have that s is equal to v plus u all upon 2 into the value of t is v minus u all upon a. So once you open that bracket, s will become v plus u into v minus u all upon 2a. Now this is a difference of 2 squares. V plus u multiplied v minus u is difference of 2 squares. So when you open that bracket, what you are going to get, this bracket numerator, s is going to be v squared minus u squared all upon 2a, right? That's the value of value of this opening bracket. So now when we cross multiply to make v squared the subject, we will now have that v squared minus u squared is equal to 2as. And then if I make v squared the subject, we have that v squared is equal to u squared plus 2as. So this becomes a third equation for a body undergoing linear acceleration. This is equation number 3. Make sure you note down all these equations because they will be very handy, including this equation I can call I. These equations will play important role for us in our studies. So make sure you note them down because we'll be using them. Now let's talk about motion in the vertical plane. Let's change this to vertical. So if the body is now undergoing vertical motion, purely vertical, like falling from a height or rising up, these following modifications will be applied to the already existing equations. We are not generating new equations. For instance, we will just make use of the equations we have, but then we apply the following modifications then. So let's see how that will be done. Okay, so for vertical, we are going to have the following modifications. You know that when we are discussing about vertical motion, the vertical distances are always referred to as heights. So we will change our distance to height, right? Because vertical distances are called heights. Another modification we will need to make here is that when something arrives to to a maximum vertical height or to a maximum height, at that final point, the velocity is usually 0. Because when you throw something up, if it reaches the maximum height, then it will rest for a while before it starts falling. So once it is going up, it gets to a maximum height, rests for a while, and then it will start falling. So because of that momentary rest, we know that velocity at such points is usually 0. The final velocity for such cases, once it is resting, so the final velocity is 0. And then our acceleration that we are using in this our equation, we change to gravitational acceleration, because a body that is undergoing vertical motion is under the influence of gravitational acceleration. So the acceleration we will use will be gravitational acceleration, that is acceleration due to gravity, which can be positive or negative. Positive is when the body is falling towards the center of the earth, falling, and that is a positive acceleration. It means that it is increasing. That is the acceleration of the body is an increase. But when it is rising up, then the change in velocity in that case will be a decrease. So it will be a retardation, and the body will be falling against gravity. So it will be a retardation. So for a body rising up, we use negative. For a body falling down, we use positive for acceleration due to gravity. So let's apply these changes to the equations we already have. So what will happen to those equations is the first equation where we have that V is equal to U plus AC. That's our first equation. So when we change the values, the only thing that needs changing here is the acceleration. We change the acceleration to gravitational acceleration. So our equation changes to V is equal to U plus or minus GT. Remember, we will choose plus when the body is falling, and you choose minus when the body is rising. So this becomes another equation 4, right? So this equation is for vertical motion. Then we will now get our next equation from the second equation we derived, second main equation. And what is that second main equation? The equation where we have that S is equal to UT plus half AT squared. So we apply these changes to this equation. What will happen is that our S will change to be H, because our distance is now height. So H is equal to UT plus or minus, because we want to change our acceleration due to gravity, we change this sign to positive or negative of half, then GT squared. That's how this particular equation will change and become this. So the new equation we have is now equation 5. UT is equal to H is equal to UT plus or minus half GT squared. Okay, now this equation we can extend it to discuss about maximum height. If the body rises to a maximum height, so when that body gets to a maximum height, what will happen to it? If it is going up, then we can change any of the equations to according to what we have. Okay, now let's equally talk about the final equation where we have V squared is equal to U squared plus 2AS. Let's change this equation again according to these parameters. So we have that V squared is going to be U squared plus or minus 2. This A will change to G and this S will change to H. So V squared is equal to U squared plus 2GH. Now, and that would be the equation 6. Sixth equation. Remember, you need to keep note. This is 5 and this is 6 for us. Remember, jot down these equations because we are going to use them shortly. Now, what can we do from this equation? We can use this equation to derive the value for maximum height. You know, when the body gets to a maximum height, If you throw a body up, when it gets to a maximum height, the final velocity at that point is 0, right? So we can change this squared to 0. Squared is equal to u squared. Now, because the body is rising up, we are going to choose negative minus 2gh. And then let's change the h here to capital H because we are talking about maximum height. Let's change it to capital H, right? So once we rearrange this to make h the subject, we are going to have that 2gh is equal to u squared. And to make h, that maximum height of the subject, we'll have that h is equal to u squared upon 2g, right? So that will be the value for the maximum height. H is equal to u squared upon 2g. That's dividing through by 2g. Now this. So this is when you throw a body. It's not inclined though. The body is not inclined. Just throw a body up, and then when it gets to a maximum height, this formula will give you the maximum height the body can attain. If u is the initial velocity and then g is gravitational acceleration of the body. So we can call this equation 7. Now we have discussed motion in vertical plane. Vertical. We just discussed vertical plane. Then motion in horizontal plane was what we discussed before. So, but in reality, bodies undergoing motion don't usually select either vertical or horizontal motions only. Many bodies don't do that. When they are in motion, some bodies will usually combine both vertical and the horizontal motion. So we'll now talk about when the motion is inclined at an angle. So at this instance, the body is not just undergoing a vertical motion or a horizontal motion. The body is undergoing both vertical and horizontal at the same time. So the motion of the body is inclined, which we describe as the projectile motion. So we'll discuss that right now.